After IPv4 comes IPv6, also known as the next generation of IP. This was created in order to address many of the inefficiencies of the original version, and this started being developed very quickly after the dawn of the internet, because very quickly after the dawn of the internet, we realized that the IPv4 address space was not going to work. The classical system had already wasted a ton. We managed to get most of those back through some fancy manipulation tactics and network address translation, things like that, but it was still very inefficient. Whoever came up with TCP/IP for the DoD thought 2 to the 32nd power would be enough IP addresses. Well, that's only like 4.3 billion addresses, not that many. And so that was not even close to the amount that we would need. So IPv6 sought out to fix that. That was one of the issues, a limited number of IP addresses. Another issue is routing being difficult to manage, so IPv6 set out to use a global routing prefixes and things. Host configuration is complicated, not overly complicated, but does require a network service, whereas with IPv6, we can get full host and device configuration without DHCP. There's no inherent security in TCP/IP. That was thought of when IPv6 was developed in terms of packet headers, and that goes with quality of service too, being able to differentiate different packet types from others to prioritize, say, voice or video data over regular file transfers, things like that. The first book I read on IPv6, or I shouldn't say read, I don't think I made it all the way through it, but I got a good bit through it, and it was written in 2002 or 2003. So this has been around for a long time, but the vast majority of us will still sit down at every computer we sit down at will have an IPv4 address. A lot of them will have IPv6 addresses also, but usually those are just kind of like the self-generated ones. The vast majority of companies have not gone full-on IPv6, and while you'll see it from ISPs and things like that, it remains one of those fringe kind of topics. Do we need to know it? Yes. Do we need to be able to recognize these IP addresses? Yes. But it's highly unlikely that you're going to be utilizing this, on a day-to-day basis. So the IPv6 advantages over IPv4 was a larger address space. It increased the IP address length to 128 bits. Okay, so instead of 2 to the 32nd power, it's 2 to the 128th power. And you might be thinking, well, that's just 4 times bigger. Nope, that's not how the binary numbering system works. From 4 to the 32 power, you just went from 4.3 billion to 8.6 billion. And then you go to 17.2 billion. You're doubling the number every time. Safe to say, 2 to the 128th power is a number that will usually glitch out any calculator that you put it into. It is an insane number of IP addresses that should never be depleted. More efficient routing, simpler host configuration, not using DHCP, built-in security for things like TLS, built-in quality assurance, your prioritized delivery support, I'd mention this, and that redesigned packet headers for more efficient processing, more extensibility, the future of the protocol. Okay, what's really important here is that we be able to recognize IPv6 addresses, and we'd be able to potentially just tell what type they are or distinguish between the different types. Those are going to be your most important things. So it uses 128 bits instead of 32. It does not have the concept of a subnet mask. Okay, instead, the default is just split it right down the middle. 64 bits for network ID and 64 bits for host ID. There will be the prefix, which is like your CIDR notation, but the vast majority of the time it's just going to be /64, which just means 64 bits make up the network, the other 64 bits make up the host. Now, because it is a 128-bit number, it's written in a hexadecimal notation because the addresses would just be ridiculously long. And there are some rules for this. Basically, the way hex works, if you recall from our chapter 1 looking at the numbering systems, 4 binary digits can be represented in a single digit of hex. Okay, 4 binary digits. So if 4 binary digits can be represented as 1 hex digit, then that means 4 hex digits would represent 16 binary digits. Okay, so that's what we're going to have: 16 binary bits separated into 8 groups, but they're represented in hexadecimal notation. Okay, so you see the first one, which is you've got 4 full groups there of four digits each. However, notice two of those groups are all zeros. So in the next example, the next bullet, we see the 4 zeros being lessened to a single zero. This is called zero compression. And then in the final example, we see that we can go beyond that and we can do double colons. The double colons, along with removing all leading zeros, can make these addresses a bit more readable. One rule about the double colons is that they can only be used once, because that's the only way you would know how many groups had been compressed. 3 different address types for IPv6: unicast, multicast, and anycast. And unicast is the equivalent to an IPv4 unicast address. That's just one-to-one communications. Multicast is equivalent to IPv4 multicast. What's the anycast? Well, it's a special multicast address types. It's typically used between routers and clients and whatnot to basically communicate things like default gateways, subnets that they're associated with, things of that nature. The mail servers on the subnet, the DHCP servers on the subnet, there are other things as well. Neighbor discovery is a set of messages and processes that allow neighboring nodes to determine relationships with one another. So when a node connects to the network, it would communicate via anycast to its local router to discover the prefixes that the router is associated with, in other words, the other subnets. It's used to ask the router if it should auto-configure itself or go through DHCP. Neighbor discovery is used for address resolution, resolving MAC addresses to the IPv6 addresses, as well as determining if somebody's already using an address. So this neighbor discovery, which is multicast 100%, is used to do all the things that broadcast was used to do in IPv4, making it more efficient. Let's talk about the few different kinds of addresses. Global unicast addresses are equivalent to IPv4 public addresses. They're globally routable on the internet, and they're designed for hierarchical routing. You've got some fixed numbers here. Okay, so the first 48 bits, the first number is fixed. That's why these numbers will always start with a 2 or a 3 if they're a global unicast address. 001, if you look at that in the binary of 4 digits, that's going to be the 2-bit. So it will always at least be 2, if not 3. Then you have a global prefix, which is your organizational ID, combined with a subnet ID. That makes up your first 64 bits. The first 64 bits is the network ID, and then the interface ID is going to be the host ID. Then we have unique local unicast. Unique local unicast are the equivalent to private IPv4 addresses. They have a 40-bit global ID that you would use for the entire organization. So the first, it's always going to be FE. So 1111 is F. And then we've got FD is how these will always start out, because those first 8 bits can't change. Your global ID plus a subnet ID, that's going to be your organizational ID. Okay. Now, you might be looking at this going, what is this? A 40-bit? This identifies your organization. Why did they do this? Here's the exact reason why they did this. In situations where you have like acquisitions and mergers, the problem with IPv4 is that there were only 3 private ranges. And most people didn't get too fancy about creating subnets and, higher in that range or whatnot. So a lot of organizations out there have the address space of 192.168.0.0 or .1.0. And I've had situations where it conflicts. You're trying to merge 2 organizations and they've got addresses that conflict. Or you're trying to get somebody to VPN this is where I saw it, VPN from a home network that uses that address space to a company network that uses that address space. And we've had to have situations where we had to re-IP things because of that. This is supposed to make it simpler. You have 40 bits to come up with a unique global ID. These are private addresses, so nobody else is going to see this. You can come up with whatever you want, but you've got 40 bits to do it. And so if you come up with something that's fairly unique, you shouldn't have issues merging with other companies if necessary. And then that still gives you another 16 bits for the subnet ID, so organizations can create as many subnets as they want, and they can maybe be a little bit more logical as well. So these do replace one of the original IPv6 addresses called site local. Those don't actually exist anymore. Then you have the link local addresses, and this is actually the one that you're most likely to see. These always begin with FE80. They're the equivalent to the APIPA IPv4 addresses, 169.254. And they're unique to the local network. They're used for neighbor discovery. They're always automatically configured. You will see them. Sometimes you can see them in response to ping. You can see them in your own IP config, but you never actually have to configure them. So if all you see is this has always been if you're only using link local addresses, then you're not actually using IPv6 in the true sense of the word. If you're using unique local unicast addresses, then your organization has actually deployed IPv6. IPv6 has special addresses as well. All zeros or just : that's the equivalent to the IPv4 address of all zeros as well. It's only ever used as a source address. It just means it's unspecified. The loopback address, which is the equivalent to IPv4's 127.0.0.1, is all zeros and a 1 at the end. That's just used for testing the local IPv6 stack. You can see an IP config there, and the link local IPv6 address of FE80, like we said, that's that automatically generated one. Now, we mentioned one of the things in IPv6 that's easier is the auto configuration capability, because you can do it with or without DHCP servers. Stateful configuration uses information provided through router advertisements and DHCP servers. So basically the host comes online, it communicates via neighbor discovery with the router to identify the networks it's connected to, but the router also has a flag to tell the host whether to try to get an address from DHCP or to get an address from the router. That's stateless if the router's just giving you that information. And the host ID is always in an EUI-64 format, which is essentially padding the MAC address with 16 extra bits to get you to 64 bits. A DHCPv6 server would be configured with an IPv6 scope that assigns network ID to the client and then assigns the host portion or the interface identifier. Those are randomly assigned, and they are assigned by a server on the local network. So the biggest deal with IPv6 in just being able to tell the difference with the IP addresses is that it's written in hexadecimal. Okay, so, but it is still a 128-bit binary number, but nobody wants to write out 128 bits. So we're taking advantage of the fact that in the hexadecimal numbering system, 1 digit compares to 4 digits in the binary numbering system. Now, if you're not following that, let's watch here. Remember, what are the possible values in hex as base 16 are going to be, there's 16 values, right? 0 through 15. That's because it's base 16, there are 16 values starting with 0, so it's 0 through 15. Now we know that 10 is A and 11 is B and so on and so forth, and 15 is F, right? Or going all the way up to 15 being F. And that's just because we need a single digit. Okay, let's think about binary though. Binary is a base 2 numbering system. And I'm just going to speed it up here, and we're going to say it's base 2, and we know that we've got the 8, the 4, the 2, and the 1. So there's 4 binary digits. And if I had all zeros in those 4, and if I had all ones, what would I have? Well, with the 0, I would have 0. With the ones, I'd have 8 plus 4 plus 2 plus 1 is 15, okay? So 4 binary digits can be combined into a single digit of hex. So if I see a starting address like FD00, each of these is going to represent 4 binary bits. And remember, it's always the 8421 bit in this case. You're never dealing with the 128 side. It's always the right-hand side because you're looking for values of anywhere between all zeros and all ones, okay? So let's just say if we needed to convert the hexadecimal number FD, we would just deal with individual digits, okay? So F is 15. So that's 4 binary ones. And then I usually separate it. What is D? Okay, well, 10 is A, B is, 11, 12, C, 13 is D. So we would need 13. So we would need the 8 and the 4, not the 2 and the 1. Okay, again, I'm just looking at these numbers right here. Let's get rid of those. Okay, as I'm converting. And then what's all zeros? Well, that's 4 zeros, and that's 4 zeros. But again, this is the binary representation of it. That is the hexadecimal representation. We use the hexadecimal representation because it's going to be quicker. All right. So, with hexadecimal, we, technically, and I'm just gonna make some things up here. Okay, so that's 4. We're gonna have more. Okay, so that's what we would have. We would have 1, 2, 3, 4 parts of the address that represent the network portion and 4 parts of the address that represent the host portion, assuming it's 64, okay? So again, you got to think about each one of these is 4 binary bits, so each of these grouping is 16 bits. And so there's 8 of them. 8 times 16 is going to get you your 128, all right? Anyway, we've got different kinds of addresses, but what's probably the most key is what you can and can't do from the perspective of leading zero. So here's what you can do. If I were to try to write that address in a nicer, cleaner format, if I could type. Okay, so we can do that 5555 1:1. Okay, we've done a couple of things. We can always eliminate any leading zeros. Okay, so we can just get rid of those, and that's what we've done down here. Always can do that. Can also double colon on any groups that are all zeros. Okay, so you can do the double colon, but as we said, you can't do that twice because knowing what I know here, we got 1, we got 2, 3, 4, 5, 6, 7, 8 groups. I've already got 8 groups, so I know that it's 0. If this was shortened, let's just say that was all zeros too. Well, then again, it can only be used once, so I would know then that actually was like that. Okay, there was 2 groups of zeros. That's just important in understanding the length. And you're always going to write it with that CIDR notation, which they actually just call prefix notation. And 99% of the time it's going to be /64. All right. So let's open up our terminal here. Oh, that's our notepad. Thought I had it open still. Apparently not. Okay, let's open up the Windows terminal. ipconfig will show you IPv6 addresses as well if you type it in the full command. Okay, so there's our link local address, FE80, followed by a bunch of zeros, and then 1, 2, 3, basically 4. Don't worry about that. That's getting into just how internal traffic works on a subnet. So you don't have to worry about that percentage notation when you're looking at this. But there's 3 groups of zeros that have been compressed there. I can tell because there are 5 additional groups. We know it's 3 groups of 0. Now you can set IP addresses. You can configure those IP addresses either through DHCP, or you can configure them through doing it statically. Okay, so let's right click here and go to Network and Internet Settings. All right, and all I would need to do is just click Edit here and change this to manual And as soon as I change it to manual, then I can choose IPv6 and I'm going to be able to type in the address. Okay. Now that's a little bit different than Windows 10. Windows 10, it's the same thing. I mean, you get there the same way. You go into, but you got to get all the way into network connections in order to be able to view it. Okay. So just keep that in mind. I mean, basically you're either saying obtain this automatically from a client perspective and it'll obtain it either from the router or the DHCP server, or you are statically configuring it. As I said before, if you go in and you see this, then yeah, we're using IPv6 because technically there's a few Windows services that will utilize IPv6. IPv6 is being used out on the internet as well. So, I mean, it's being used, but if it's FE80, it's almost just like a MAC address. It's an automatically generated address. It's only used locally. If you see FD00, then you've actually been given a local unicast address. And if you're at home maybe and you do an IP config, it's possible that your ISP will have given you an IPv6 address. Okay, those are always start with the numbers 2 or 3. So biggest thing is just how the addresses get assigned, being able to differentiate the addresses, know what is appropriate zero compression and what is not, how to write them out, how to convert them into binary if necessary. Those are going to be your important testable concepts in relation to IPv6. All right, in this demonstration, we're going to do another little just objective check. The CompTIA objectives are, they kind of go on and on in certain areas. It's possible for us to miss certain things. I do this for a couple of reasons. Number one, to make sure we didn't miss anything, or maybe because I know we did, and this is an easy way to fit it in. But number two, it's to get you familiar with the idea that you're learning this information to use it in the real world. But a lot of it is conceptual and or very particular things of memorization, and you're learning them first and foremost to pass the certification exam, right? To validate your knowledge. So that means you need to be familiar with these objectives. If you don't already have them, please go out and get them. You can just search for them very easily. They are available for free right on CompTIA's website, which is comptia.org. Okay. So in this section, we've been talking about cables, connectors, IP addresses. So I just want to hit those main objectives. Let's see, that's the first chapter. So, okay. So we've got, you can see, summarize the types of cables and connectors and explain which is appropriate for a particular solution. So that it means that not only do you need to know what these are, but you just need to know when you would use them. Okay, so twisted pair is typically going to be used for client connections. Cat5e is going to be required for gigabit Ethernet. Cat5 for fast Ethernet, which is only 100 megabits per second. So typically on client connections, that's what we're going to be dealing with. But then you've got, server, more high-end networks now, getting up into the upper categories. We see the 568, 568B wiring standards. Your, coaxial, twin axle, you wouldn't be using those for client computers. Difference between single mode and multi-mode, various connector types. Okay, I did not mention the angled physical contact versus ultra physical contact, APC versus UPC. It's really how the fiber itself is cut. You can just do a quick Google search for that, but let's do APC versus UPC, and you're gonna see that, and it's just a different graphic. This is just one that I forgot to put in there, but you see the main difference is the fiber end face. Okay, UPC are polished and they have no angle; it's a flat. APC actually has an angle, at an 8-degree angle. Typically UPC are blue, APC are green. That kind of doesn't matter. If you want to see more information, fine, but that's really all that is going to be necessary for the exam. It's just the different cuts. Okay, we've got the different transceivers we talked about, and connectors. We talked about all of those, where they might be used. Your cable management, your copper standards. Now in here they identify, the Ethernet standards, copper and fiber. And here they identify maybe more than what we had. I don't remember if we had all the FX, SX, LX, those kinds of things. I would go through those since they are explicitly listed. The big thing is going to be your speeds, which is very easy, right? 40G is 40 gigs, 10G is 10 gigs, 1000 is 1 gig. So the speed is 1, but then the difference between multi-mode and single mode and multi-mode fiber, okay? That's where it gets important because remember the single mode fiber has the potential to go miles, whereas the multi-mode, no, 500 meters or less. So that would be a situation where they might be asking you which one to use, and you got to be able to recognize those standards, okay? And that media specifier specifically. And then different types of wavelength multiplexing, which is used for multi-mode fiber, and that's giving us the ability to have multiple signals on the wire. All right, then we talked about the class or the IP addresses, and I think we did all of this. A variable length subnet mask, VLSM, is not a term that I used, but anytime you're in classless routing, that's technically what you have. It just means the subnet mask can be variable in length. They don't have to all stop on the decimal points. And so along with that, we get CIDR notation, right? All right, I mentioned all the other things there. Okay, maybe a couple terms I didn't mention here. So IPv6 is a dual stack. It means that every system that uses IPv6 has both IPv6 and IPv4 in a dual stack infrastructure. IPv6 does support being tunneled through IPv4 networks. These are like compatibility standards. Your router advertisements and your stateless address auto configuration, SLAAC, that is a term that is just referring to the stateless configuration, meaning I can get an automatic, we talked about this, meaning I can get an automatic IP address without using DHCP, right? I communicate with the router, and either the router tells me what to use or how to set it up, or it tells me to go use DHCP. So I don't think I mentioned that acronym. Virtual IP addresses are just virtual IPs, but subinterfaces that shows IPv6 has, remember we saw the IP address and then the percentage and then a number, those are your sub interfaces. They're automatically generated and just used as a part of the protocol. So you probably don't have to get that deep into that. And okay, I believe that's it for this chapter. So like I said, just want to do a quick objective check here before we close out chapter 2. And then, as I said, remind you all, keep your eyes on these objectives as you're studying for the exam. Make sure that you are able to give answers or anything that might appear there. In this chapter, we looked at some really more network fundamentals. The things that are required in order to connect to a network would be a particular type of connector and cabling. So we talked about Ethernet cables, we talked about wireless connectivity, fiber optic cables, the different cable types, and the connectors that are associated with them. Now we also need a protocol, a language of communication. We need port numbers that are used to identify different applications and services on various systems across the network. And so we discussed those commonly used ports and how those were important to memorize for the test. And then you also need an address. I need to know where to send packets. I need to know where the packets originated. And so that's where IP addressing or protocol addressing comes into play. TCP/IP is a suite of protocols, but Internet Protocol, IP, v4 and v6 are the two that are used to apply addresses. And so we talked about public versus private and subnetting, and how to use the subnet mask to differentiate between the two portions of the IP address. All of that very important information really from a configuration and troubleshooting standpoint.